Welcome students, I'm Tanmoy. I welcome you all in my channel Chemistry Chemistry of Molecules. So this is a different type of lecture today, that is methods to convert cis-alkene to trans-alkene or trans-alkene to cis-alkene. Okay, actually this is a very general method, so that I will discuss. There may be some other special techniques, but I am not going to focus on that because I believe first let me give you a general thing. So if you think I missed any point or missed any method, please mention it in the comment box. So in future I will make video on that. Okay. So today we are going to discuss this conversion of cis to trans or trans to cis-alkene using three different methods. For example, first one is via vicinal dibromide, then alkyne, then that. Second is via epoxide triphenylphosphine method, and third is via hydroboration followed by tosylation and elimination method. Okay. So let's start. First method is via vicinal dibromide, or you may consider this is a geminal, whatever. But for example, since I told that cis to trans, so let's one alkene, that is a cis. So if we react this with bromine in CCl4 carbon tetrachloride, what is done? Through bridge bromonium ion, it resulted in vicinal dibromide with anti-orientation. I have already made a video about the bromination of alkene. So if you want to learn details, please go through that. And by the way, I want to mention that I am not going to give details understanding of this processes here. I have made video, please go through that. I want to make it as short as possible. That's why I am not going to explain the mechanism again. So fine, so next step is that if you put any base like sodium alkoxide, mild base, so what we know that it will result in alkene via elimination. So let's think that there may be this vinyl bromide, and if you give very strong base like sodamide NaNH2 like that, so what it will result means there is another hydrogen. Okay, so ultimately because of this it result in alkyne. Let's consider this as a methyl, it will be helpful. So these are two methyl. These. So methyl. Let's consider this as a bromine, and this is the methyl. Fine. So ultimately this will result methyl C triple bond C methyl. Okay. By the way, similarly, if you take cis1 also, under bromination, it will produce dibromide, means whatever, in presence of NA1, ultimately it will result in this molecule. And in presence of base and sodamide, ultimately the product will be alkyne. So that's why I told this is alkyne medicated. So our target is to prepare alkyne. Now, this alkyne is, so whatever cis or this is trans, this is cis, whatever the product ultimately will be converted into alkyne using a generalized method. So if you treat this alkyne with Barch reduction method, what is this? Barch reduction, it will result into a trans-alkene. Okay, this. So if you started with cis, then you want to get trans, then do the Barch reduction. What is the Barch reduction? That is sodium in liquid ammonia. Okay. By the way, I want to mention that in case of Barch reduction of alkyne, actually what happens? First, this terminal alkyne takes an electron which is generated from sodium and stabilized in ammonia, resulted into a transform. This is the radical and this is the anion. They remain in trans orientation in order to avoid the repulsion. And second step, for protonation, here ammonia molecule supplies the proton. Generally for Barch reduction, what happens? Alcohol produces proton, but this is actually, this lone pair is in sp2 orbital. That's why it is sufficiently basic that it can abstract the proton from here. okay, and result into the protonation. Second step, again another electron, then here there will be a negative charge that will abstract proton from another ammonia molecule, and in this way the two-step reduction happened and two protons come. So this proton come from ammonia molecule. But by the way, one important information, please keep it in mind. So if you do the Barsh reduction of benzene, means same sodium in liquid ammonia, and it resulted into a radical anion, means this is radical, this is anion. So for this needed ethanol or any alcohol, tertiary butanol, to be protonated. Why? Because this negative charge is in delocalization with this two double bond, means the charge density is less here compared to this, although this is a sp3 carbon. So don't be confused, this is a very important concept, I believe you must know. So okay, fine. Now we have discussed how this alkene could be converted into this acetylene will be converted into the trans alkene. So now if we want to get the cis alkene, what can we do? So we can do reduction by Lindlar catalyst. Lindlar catalyst. I have also discussed about this in my previous video. Please go through that if you want to details. So what is the Lindlar catalyst? Lindlar catalyst is palladium, hydrogen, and along with that for surface area and actually reducing them is palladium hydrogen. But if we use only palladium hydrogen, this will ultimately result in alkane preparation. But we need to stop it is in alkene preparation intermediate stage. For that place, first one we need barium sulfate or calcium carbonate, which increases the surface area, and second we need quinoline or sulfur as catalyst poison. This quinoline act as a catalyst poison such that this reduction stops at this alkene phase. And since this reduction is on a metal of this is the palladium surface, this so hydrogens are in this way adsorbed, means hydrogen adsorbed and split it into, and we are reacting this alkyne, so hydrogen transfer happens from the same side, that's why it results in cis alkene. Okay, so this is the difference. So now the question is, if you are advised to prepare, if you are started from cis, then do the same procedure and ultimately come to acetylene, and from cis you want to get trans, then do the Barsh reduction, or you have started from trans, follow the same procedure to prepare alkyne, and through Barsh reduction, through Lindlar catalyst reduction come to the cis one. So this is the strategy to prepare the means interconvert the alkene in through different chemical transformation pathway. Now the second one is via epoxide. So as mentioned here, this reaction, in this case alkene will first converted into epoxide and then it will be converted to again to the another alkene. Okay, so epoxides are nothing but a 3-member cyclic ether. So let's start. For example, let's start from trans one. So actually this 2-butene I have taken as a model substrate. So don't think that every case this is used, other not used. Just as a model substrate to make the thing easier I have taken. And for epoxidation, the reagent means there are many reagents, but in this case I am going to use this reagent, which is named as metachloroparbenzoic acid. Metachloroparbenzoic acid. In short, MCPBA. Metachloroparbenzoic acid. Why metachloro understood this is meta? Why parbenzoic acid? Because there is a peroxyl linkage, and this part is responsible for the oxidation of the double bond, means the epoxidation. So what it does, this resulted in a epoxide formation. So this is methyl. So epoxide means ring, it should be same side. So fine. And another thing, what happened with this MCPBA? It resulted into metachlorobenzoic acid. Okay, this peroxyl linkage gone because oxidation happened here. Now what is the next step? The next step is reaction of this with triphenyl phosphine. We know that triphenyl phosphine is a soft center, means it is a nucleophilic center. So softness is associated with, so it will attack, and since epoxide is an electron deficient, because this is delta plus, oxygen is delta minus, so electrophilic center, this has electron density delta minus, so it attacks and it opens up. So what it produces? It produces this region. So this is the methyl. So this, let's consider this PPH3 is in front phase. So what will be the O minus stage? It should be in back, O minus. Now this is the thing, and PPH3 will have a formal positive charge on it. Now we know that this CC bond can rotate. So what it will do? It will undergo CC rotation. Sorry, it undergoes CC rotation. So CC rotation. So what is the consequence? Let's draw it. So this methyl and PPH3, means hydrogen is in the back. Here hydrogen is in the front. Fine. So this is metachloroparbenes, this is PPH3 plus, and this is hydrogen. So if it rotated, so from the back it will come to the front. Now question why? I will explain. O minus. Actually I want to say that it is possible that this rotation can occur. Fine. Now why? Because after that it will attack here, and what is the consequence? If it attacks, then it forms a 4-member ring. What do I mean? This is the methyl. So hydrogen is back, and in front side I should draw it properly. In front side there will be PPH3. We're having a plus charge, so if it attacks, it neutralizes. And how this can happen, or why this can happen? So this thing can happen because phosphorus can expand valency to 5 because of d orbitals, having energetically accessible d orbitals. Okay, and 4-member ring this is. We know that 4-member is in strain, but larger size of phosphorus reduces the ring strain. Okay, and third point, phosphorus oxygen bond is stronger, PO bond stronger. So this is the reason, that's why this ring can form, and when it forms there is a cleavage. This comes, it goes. So what it results? See, this methyl is in the same side, hydrogen is in the same side. So if such thing happens, so what it resulted? This methyl, this, and see, this bond comes here, so our CC double bond is formed. So this methyl is this, hydrogen is here, and along with that what is formed? Along with that one reagent formed, PPH3 double bond O. See, phosphorus oxygen bond energy even higher, and this is the driving force for this reaction. So see, because of this higher bond energy, a trans alkene, ultimately you can achieve a cis version, from a trans to cis. So this is the uniqueness of this method, and the most interesting point is that this happens because of the higher bond energy of phosphorus and oxygen, means PO single bond. PO double bond formation is very facile. That's why, and this is so much facile that even the 4-member ring formation is also possible for the reaction. Okay, so this is the second thing we have discussed, and let's discuss about the third method, that is via hydroboration followed by tosylation. So let's see, take from trans. Arbitrarily, there is no preference for trans. So if you do hydroboration, we know hydroboration we used to do using BH3 in some inert solvent, or actually the reagent is B2H6, which is converted into 2BH3 molecule undergo reaction. I have already made video about hydroboration, so please visit if you if you want to know more. So this, and what it resulted ultimately, first step hydroboration and second step. So step 1 is hydroboration and step 2 is sodium hydroxide, hydrogen peroxide. Okay, first is hydroboration, second is oxidation. So hydroboration, oxidation, both. So ultimately what is expected? We know that same site. So if this is methyl, this is methyl, so hydrogen and, for example, hydrogen and hydroxyl OH will be in same site. Okay, so here also this hydrogen is back, hydrogen is back, this is the thing. Fine. So this is now if second step is what is the hydroboration and tosylation. So tosyl chloride, what does it actually looks? So para-toluene sulfonic acid. Why tosyl chloride, not simple benzoyl acid? Actually it is benzene sulfonic chloride. Why? Because this tosyl chloride is a solid reagent. But if you think simple benzoyl chloride is a liquid reagent, storage and handling a solid reagent is always better compared to this, and pyridine act as a base. Okay, this is also abbreviated as TSCl. So what happens? This alcohol attacks here, it opens up, comes back, and chlorine leaves as a good leaving group. Fine. So what it result? This result in this methyl, this hydrogen is in the front side, this is in the back. So I am not interested because see, both are same. So no need to focus on this. We should focus on this side because this is three substituents are different. So this is methyl and OTS. So this is will form OTS. So this part is considered TS. Fine. Now if we put a base, okay, even you consider like sodium ethoxide, like that in ethanol. So what happened? This OET minus first abstract this these OET minus abstract the proton anti to this. Okay, so if it abstracts the anti-proton, so okay, it is better if I provide you another thing. I think it will be better. Some other substituents if I provide. For example, this is X and this is Y. So instead of this hydrogen, this is methyl, the same side, opposite side. So okay, this is hydrogen, fine. So this is X and this is Y. So this is where this is X and this back side is Y. Fine. Now it will be easier. X and Y means two different substituent. I want to focus. So right now, see, actually this hydrogen came from this BH3. Okay. So in cis orientation. So if it is in cis orientation, what is expected? If you want to do elimination, there is no problem that hydrogen could be abstracted, but for elimination, this orientation of this hydrogen and these OTS must be trans. Why? Because, so if you want to see, this hydrogen is abstracted, so there is a negative charge generated, and there is and this negative charge, okay, better to give you explanation. So this X and this is the H. So because if when this hydrogen is abstracted, the electron pair in the sigma orbital can participate in the conjugation with the sigma star of this CX bond. X is the leaving group. For example, here OTS. So they can conjugate. So that is the reason why it is essential that this hydrogen and this X must be in anti-orientation. And since it's a CC single bond, so it can rotate. Okay. So if it can rotate, what can happen? First of all, so I am not saying that abstraction is possible, but there will be no phase. So first, better to say that let it rotate, means this part will be, let's keep this part same, methyl X, because only hydrogen is abstracted, this is the H, fine. So other part, rotate means it goes to back. You can think like that, rotation in this direction. So what is back means OTS. So this methyl whatever is in the plane is expected to be this direction, this, so it's expected above. Okay, above. And another thing is it will come, this is the methyl and this Y will come here. Okay, so right now these are anti-orientation. This, so what can happen? That, okay, what can happen? These two could be eliminated because this hydrogen could be abstracted by this base, followed by it will come here and this OTS will leave. Fine. So what is the consequence? Consequence is an alkene formation with, see, this methyl and Y is in anti. Okay, and this X, because X is below and methyl is above, X and methyl is in anti. This, you get it? How I am saying? These are in the same plane, so anti, and this is above, this is so, this part, these are anti. Same plane you can directly see anti, and this is from plane, you have to, from 3D you have to understand. What we have started? We have started methyl opposite orientation. I am not saying cis-trans because it depends, or actually EZ conformation is better to describe this. But see, methyl previously anti, right now methyl cis. So this is the third method for the conversion of cis into trans. Or here just forget about this X and Y. You can say this is a trans to cis. Okay. So this is the overall discussion for three methods to convert cis into trans or trans into cis. Similar thing will happen if you start from here and follow the same thing. Because the reactions means these hydroboration, it's a residue-selective as well as stereo-selective. That is the uniqueness. That's why this would be achieved. Even elimination, this is also anti. By the way, another information, another thing that you may think that, sir, there is methyl means you can say this is a CH3. Fine. So there is also proton. So why not elimination can happen? Actually, this thing could be explained in Selective rule. Because Selective rule says during the elimination, chances are there will form, but that alkene will be produced as a major product which is more substituted. If the proton abstracted from here resulted in more substituted, but if it abstracted from here, see, it's a less substituted, ultimately CH2 will be produced. So, and since the transition state is alkene type, means product type, and that's why if the alkene having more number of hyperconjugative hydrogen, for then it's more stable. So the energy of activation associated with this terminal alkyne is higher. Energy of activation is higher for this terminal because it's less stable, because less number of hyperconjugative hydrogen. That's why this path will not be followed. In contrast, known as Selective rule. Okay, so this is the overall discussion for this process. So thank you everyone for listening. I hope this video is useful for you. If it is really useful, then please help me to grow my channel. First of all, subscribe my channel, Chemistry and Mystery of Molecule, and please press the bell icon to get the notification of every single video I upload. Secondly, share this video among your friends so that many people will be benefited, and I will be very happy if my work is beneficial for many people. And thirdly, please like the video and make some good comments. Your comments are the encouragement for me. But if you think it is not very good for you, or you want some improvement from my side, please mention it in the comment box. Your criticism or suggestion is helpful for my improvement in future, and if it is, then I expect that I shall be able to make further better videos for you, and so that will be helpful for both of us. So thank you everyone again. See you in my next video. Till now, God bless you.